Hi! In this video, I'll be going through the definition of continuity in a metric space. In the previous video, we have talked about what is a metric space, which is basically a set and you give it a metric, and a metric satisfies three properties: positive, definite, symmetric, and triangle inequality. With this notion, you have examples of many different type of metric spaces, and so you just have different sets with different metrics or different set with the same metrics, and they are all different metric space. So you have two metric space, and we want to talk about the functions between them. And so we let x and y be two metric space, and we suppose that there is this point in x known as a limit point. And the definition of a limit point will be talked about more in future videos when I go through basic topology, because you see how it really ties in then to the definition of continuity of between functions. But we do not. So I'll just give you the definition of the limit point by Rudin here, but we do not concern ourselves much with this definition first. But the main idea is that it gives us a way to write a sequence, and that is very important when we talk about metric spaces which are countable in nature. Because by having this sequence, you are able to do the whole sequential criterion for continuity in real numbers. And so this limit point is really so that it allows you to keep shrinking down your space to create a sequence so that fx approaches the limit. So it's not really a big deal, but we just leave it there for you to understand for now. We'll talk more about the importance of limit points in future videos. So let's begin now with what we want to talk about in this video. So when we have a function, we say that as x approaches p, the limit of fx equals to q if there's a point q that satisfies this following property. And this property is just like your delta epsilon property in calculus. So for every epsilon, there exists a delta such that when the distance between x and p is less than delta, it implies that the distance between fx and q is less than epsilon. So like in calculus, instead of now putting the absolute value, you change it to the metric function, because you don't know what the metric is. It could be the absolute value, which is the standard metric on a real space. And so when we say that L is the limit of f at C, then we say f converges to L at C, and these are the notations. If the limit does not exist, then it diverges. And we can say that the limit is unique, and the proof is how you did in calculus. So you can check out my calculus videos, or you can just understand it from a sequence perspective. Note that FC doesn't play any role in this definition of the limit, like when we talk about in calculus, because we want to know how fx behaves approaching point P, and we don't really need to care about how at that point FC or FP matters. So some examples is when we find the limit of x approaches C of the function x, it will be C, and you can see the proof of why is so. And for the bottom one, which is more complicated, I'll leave it to you to read of how we've chosen the delta, but you can see how it is very similar to understanding limits or functions in calculus. So this is really just a recap. We'll talk more about the analysis part soon enough. And with that, because in analysis we went through what is a sequence and what is convergence of sequence, you can see the two notions look very similar. And so this is where we say that there is a sequential criterion for convergence. So the limit of fx as x approaches p equals to q if and only if you can find for every sequence that approaches p, f p n equals to q as n approaches infinity. So it means that you have a sequence now, p1, p2, all the way. Then this sequence approaches the value p. Then now you just take the image of every point and then you check whether this sequence converges down to the value q. If it does, then and it occurs for every sequence p, then we say that fx, the limit of fx as x approaches p is q. So the proof is quite easy to follow. So suppose fx limit is q, then we can choose a pn because p is a limit point, so we can choose a sequence satisfying 6 and then let epsilon be given. Then there will exist a delta such that for all the x's delta close to p, fx is epsilon close to q. And because of that, we also know that because pn approaches p, there will exist a cutoff such that pnp, p, the distance between them is less than epsilon. And so now we can find a cutoff such that fpn q is less than epsilon. Because we just need to find this cutoff so this will occur. And when this occurs, we know that this will occur. And hence, property 5 holds. And now if you assume it's false, means this doesn't approach q, then you can always find a epsilon such that for every delta there will exist a point within delta distance away from p, but fx is epsilon distance away from q. And then you just take the delta to be 1 over n for this epsilon, and then you see that for every sequence it converges to p, but fx is always away from a distance away from q, so fx can't approach q. And so we have proven the sequential criterion for convergence. And this sequential criterion for convergence can be applied to continuity, and we'll see in a subsequent video or later on. So let's define more notions first. Let's say that f has a limit at c, then f is bounded for some neighborhood of c. And really, that's because you can apply the same idea as when you prove why a sequence of function that has a limit that converges is bounded. And then you can also prove all the limit theorems from our calculus. And so I'll leave it to you to look at our calculus video for you to understand it. And so what we care about is the divergence criteria too, because we want to know when a function doesn't have a limit at a certain point. And so we say that f doesn't have a limit if and only if there exists a sequence that converges to c, but the sequence fxn doesn't converge to L. And if this occurs for all else, then it doesn't have a limit at all. And this is really because of the sequential criterion for convergence reformulated. And so let's just take a look at this example. 1 over x. So we know that 1 over n approaches 0, but 1 over n equals to n, and this is unbounded. And so the sequence epsilon xn equals to n is not convergent, and so the limit as x approaches 0 of 1 over x does not exist. Another example using the divergence criterion is to prove that the limit of sine 1 over x does not exist. And to do this, you just need to, instead of finding a sequence such that it doesn't converge, you can find two sequences that converge to different limiting values. And this will mean that because the limit, you can't have a limit that have two limiting values, it means that the limit doesn't exist. And so the first sequence we consider is sine of n pi, 1 over n pi. And so the limit of this sequence equals to 0, and when you run it through the function sine 1 over x, it will equals to 0 for all n's. And so the limit of this sequence is 0. But now you take another sequence that converges to 0, which is half pi plus 2 pi n to the power of negative 1, the reciprocal. Then yn approaches 0, but g of yn approaches 1. And so the limit of 1 over x as x approaches 0 does not exist. And so I hope you see how in calculus we just use the epsilon delta definition always. But because in analysis we talk about sequences, we are now able to reformulate the epsilon delta criterion to the sequential criterion for convergence. And everything else, the proof just follows from how we have proven it for sequences, such as the limit theorems over here. And so I hope it's not too hard to create a link between sequences and convergence for functions. And in the next video, I'll show how sequences also can be applied to continuity. And it's really an extension from the continuity that we study from calculus, and a more rigorous proof of it. So I'll chat you in the next video. See you.